All right, so yesterday we talked about the Diels-Alder reaction, and we got a little bit into the stereochemistry of Diels-Alder reactions, right? So if we've got a diene and a dienophile, and our dienophile is cis, that means that our Diels-Alder product will also have cis substituents, meaning both of those nitrile groups are going to be pointed in the same plane. And then we said if it's trans, the same concept applies. Those two groups will be trans to one another. And then with tetrasubstituted, it really doesn't even matter because you don't have stereocenters anymore. And then we had this challenge problem too, where we had substituents coming off of our diene rather than our dienophile. And so you have to account for that too. If you've got that one methyl group pointed in a different direction than the other one, you have to account for that as well in your product. And I really recommend trying to get good at drawing either the side view or the top-down view so that you can kind of see how each of the substituents is lining up with one another. But let's do another problem today. And I'll give you guys a minute to think about this. So let's practice this one. This might help you with sapling too. So I've got a methoxy group coming off of my dienophile, diene. And for my dienophile, I'm going to have an aldehyde, and I'm going to have a methyl group. So I'll just leave that as a dash, or a straight line. So what I want you guys to do is to predict what the product would be out of this. And I'll give you guys a hint, too. We've got a couple of different options. And one is correct and one is not, but I want you to see if you can figure it out with your neighbor. So one of these will have the methoxy group on the opposite side of the ring of your aldehyde. And then the other one will have them on the same side. So which one do you think is going to be the product? And then once you're done with that, be sure to include the stereochemistry for these carbons right here, too. Which one's going to be a dash and which one's going to be a wedge. So I'll give you guys a minute to work on that. Which product are we going to make from this Diels-Alder reaction? And then once you figure out which of these you're going to make, be sure to include stereochemistry as well. I'll give you guys a hint, too. When you're trying to determine the regiochemistry, try drawing the resonance structures for both your diene and your dienophile. So draw all of the resonance structures for these guys over here. If you feel pretty confident, give me a thumbs up too. I'm kind of curious how many of you guys feel confident with this one.
I will stick with my answer with confidence whether it's right or not.
That's good. Blind ambition's a good thing.
It gets me into trouble, but it's fun though. It is a fun path to take.
All right, let's get started with the resonance structures, right? So we've got lone pairs on this oxygen here. So I'm going to dump these down, and then I can dump these electrons over, right? I can't dump electrons to the southernmost carbons, right? Because I'd be violating a bunch of octet rules. So in this case, this one has a pretty simple resonance structure, where there's a double bond here, and then a lone pair here. So I'm going to bracket these off. And then underneath, what I'm going to do is I'm going to draw the hybrid structure. So we haven't done that in a while, but it's good practice. Where this is more of a dash bond, and this is a dash bond. And then we've got this methoxy group. And this methoxy group, the oxygen on it's got a partial positive, and this carbon over here has a partial negative, right? Are you guys seeing that? Right? Same thing with this guy over here. I have a resonance structure where I can kick electrons up. Oop. When I do that, the carbon underneath is going to have a positive charge, and the oxygen is going to be negative. And then we have one more structure where I can take this pi bond, move it over, and now the positive charge is down here. Let's do the same thing again with the hybrid structure. You guys thought you were done with this. You're not. So this oxygen's got a partial negative, this carbon down here has got a partial positive, and this carbon right here has got a partial positive. Do we agree on that? All right, so now what I like to do is I like to identify my sticky ends of both my diene and my dienophile, right? So we know that this carbon's going to form a covalent bond, so I'm going to highlight it in blue. Let me actually zoom in on these guys a little bit. So this carbon in blue and this carbon in blue, those are the two carbons that are going to form new covalent bonds to another carbon, right? And then on my dienophile, I've got two sticky ends, one right here and one right here. We know that we're going to connect the carbons highlighted in blue. The question is, which carbon is going to be bonded to which other carbon? What do you guys think?
Negative to positive.
Yeah, the partial negative wants to bond to the partial positive. So if we look at this, this site's going to be really attracted to that site. Okay, that gives us a really good clue when it comes to performing this reaction. So these two carbons are attracted to one another. All right, so now we've got a pretty good setup, but let's go ahead and draw our complete Diels-Alder reaction. So full mechanism. And with our full mechanism, we need to keep the right carbons facing each other. So we've got a methoxy group up here. And we know that the aldehyde should actually be flipped kind of upside down. So for the dienophile, do you guys see that?
Yep.
And that's simply because we want this, this delta negative to be attracted to this delta positive. Okay, so I'm going to dash those two carbons. They're going to face each other. This pi bond's going to hop over. I'm going to scoot this up. This pi bond's going to hop over, and this pi bond's going to hop over. So people were asking me what's some good strategies for remembering the arrow pushing. What I always do is I identify those sticky carbons, the ones that are going to form the covalent bond. I do the dashed line between them, and then I create clockwise or counterclockwise electron pushing arrows, right? You want to make sure if you've started out going counterclockwise that all of your arrows are counterclockwise. Or if you start out going clockwise, they all go clockwise. You don't want some clockwise and some counterclockwise arrows. Okay, so we've got this going. So let's go ahead and draw our product out. And then I want you guys to help me with stereochemistry as well. Let me clean this up a bit. All right, so if we're looking at the stereo centers for, oh man, my pens are going crazy here. For this position and this position, what should they be? Should one be a wedge and the other be a wedge? Should we have both dashes? Should we have a dash and a wedge? How do we want to show this? Dash and a wedge, right? Because our dienophile was trans. So we need to make sure that we represent that using the proper arrows. And does it really matter which one's the dash or which one's the wedge? No, because in this case we're going to end up with a mixture of enantiomers, so you could have either or. And you can actually draw both of them out or just draw one and write plus En. I'm fine with it either way. So let's go ahead and do that. I'm just going to do a wedge for this guy and a dash for this methyl group, and then I'll write plus En. So this is really the best way to account for regiochemistry for Diels-Alder reactions, is to draw the resonance structure for both your diene and your dienophile. Yep?
For the way that you have the mechanism drawn here on the left, would that produce the exo product? Because the electron withdrawing group on the dienophile is on the outside rather than underneath?
That's a good question. So with endo versus exo, let's go back and look at that. Endo versus exo is usually in reference to which bridgehead you're closest to, right? So endo, the part I've got drawn in blue up there, is closest to the longest bridgehead, where exo is closest to the shortest bridgehead. That only can be used as a terminology for bicyclic ring systems. In our case, in our last example, we only have one ring, so you don't really refer to it as exo or endo anymore.
Okay.
Yep.
So is there there's no preference for that aldehyde to be closer to the oxygen, it's just wherever it is?
Exactly. So the question was, there's no preference for endo versus exo with monocyclic ring systems because you can't really differentiate.
Okay.
Yep.
Once what we made was bicyclic, would the aldehyde or would the methyl be?
That's a good question. So in where is it? For the last problem we looked at, hypothetically, if we were creating a bicyclic ring system, we would want that aldehyde to be in the endo position rather than the exo. The endo is almost always preferred. Let's do another practice one, though, and we'll take a look at that. Okay, so let's do this one. This one's going to be a little bit more complicated. So this is our diene. And our dienophile is going to be pretty similar to what we had, but I'm just going to do an ester. So a methyl ester. So spend some time on this and make sure that you not only have the correct stereochemistry, meaning your dashes and wedges, but you have the correct regiochemistry, meaning the correct carbons are bonded together. And then once you think you've got it, check with your neighbor. I'm going to make this one worth 4 points. Maybe 5. This one's harder. I'll get us started with the resonance structures. we'll draw the hybrid down below too.
I saw that.
The methyl group, I forgot.
Yes.
Yeah. I'm not going to draw all of the resonance structures, but I am going to draw out the most important ones. You're welcome to draw all the resonance structures if you'd like. And then, like I said, double check with your neighbor when you think you've got the mechanism down. I hear a pin drop in here. If you and your neighbor agreed, give me the thumbs up too.
Oh, sparkling pen, you know, it's going. Oh,
I think I was on that day too. I saw it on the video.
oh, no, I don't think it does.
Yeah, they've got cool new pen colors now. See, I can do a gold pen. Technology is crazy.
We have this here, these two reactions.
Yeah.
Which ones we have?
You need to find a special use for sparkling pens. I don't know what it is yet, but
Oh, you're just showing.
So this is
This one's more different than this, that's that.
Quick show of thumbs. Sideways means you're working on it. Thumbs up means you got it. A lot of sideways. I'll give you guys another minute or so to work on this. Try to argue it out with your neighbor too. If your neighbor understands it and you don't, talk to your neighbor.
I don't like arguing with my neighbor. He's always right.
Yeah, your neighbor's the worst.
She is. She's always right. I argue.
Yeah, but she is.
My clients don't even do it anymore. I thought being wrong. It's too much of a goal line.
So
Yeah,
this
much
part
arbitrary.
here, and then this one, here. It's not, well, this is, but this,
I hope so.
that's positive. I didn't look at my drawing. But either way, that's not the terminal part. It's only the terminal part that's reactive. You have to have, remember, it has to be a cystine. So they both, it's wherever they're pointing at, the cyst part. So in this case, it's whatever cyst is. So it has to be these two.
I don't even care about it.
Because this is the anti-cyst.
The one thing I like with quarters has been NMR. That was nice. That was a nice segue away from that.
Oh, yeah, I think I see.
I enjoyed NMR. Except for that quiz I got right. Mass spec is gross.
You just have
These.
right here. This is down. So I
UV
figured
is
that
about the
because
same. Mass spec is real kind of gross, but IR.
yeah, this is the
Is that the Chem 131 teacher that came here yesterday after class? He's teaching them IR.
I think he's introducing them too.
this goes here.
All right, let's see another show of thumbs. Thumbs up if you feel pretty good. Thumbs down if you just don't get it. Some sideways if you feel like you're making progress. Okay, let's kind of stop and look at this as a class. The main thing, like I said, is looking at your hybrid resonance structures, finding those sticky ends that want to react with one another. So for example, I'm going to do the same thing I did before with my sticky ends. This is the carbon pair on my diene, and then the carbon pair on my dienophile, right? Okay, if we look on my diene, one of those carbons has a partial charge, right? The lower one. Do you guys see that the lower one's got a partial negative? Okay, so I'm going to go ahead and label this one as partial negative. And then if we look at my dienophile, one of those two carbons also has a partial charge. Specifically, the lower one's partial positive. So those two carbons are going to be really attracted to one another for the Diels-Alder reaction. So I'm going to line those up, draw my dashed line. And then this carbon's going to hop over, or sorry, the pi bond's going to hop over to form a covalent bond. This pi bond will move over, and then this pi bond will move over. Okay? So let's take a look at this. And I'm not going to include stereochemistry right now, but we're going to come back to that. And we've got this methoxy group coming off here. Okay, if we look at this, right, we've got a bunch of stereocenters coming off of here. And we've got to be able to determine whether or not there's dashes or wedges coming off of each of those positions. So in order to do this, I oftentimes like to draw...
You really hate methoxy, don't you? You keep forgetting it.
Oh, thank you.
I'm
Holy
just
cow.
gonna add it on later. It's cis trans.
Thank you. I forgot about my methoxy group here. So we still kind of need to define that a bit more carefully. But let's do the side-on view for this docking mechanism, right? So I'm just going to draw these a little bit differently down here. All right, so that's my diene. So that's the side-on view. And then our dienophile we know is going to be underneath. So I'm just going to write this as CO2Me. Can you guys see that that's my methyl ester kind of underneath? And why do I have the methoxy group pointed underneath the ring rather than pointed out away? Yeah, the endo docking, right? We want this electron withdrawing group to be underneath the ring when it's docking. That helps stabilize the transition state. So let's go ahead and do this. I'm going to highlight these blue carbons again. Right here and here. And then these red carbons are going to form, or sorry, these red lines are showing where that covalent bond's forming. So this pi bond's going to come over. This pi bond's going to move over. And this pi bond's going to move over. And then I'm going to draw the transition state too. And the transition state's a little bit funky to see. But one important thing is this green carbon right here is actually going to flop up a little bit, almost like an envelope lid. So it's going to poke up a little bit. And I'll keep everything color-coded. So we've got these blue carbons right here. The green carbon we said is flipped up like an envelope lid. And then underneath we've got this dienophile, which we said has the methyl ester pointed underneath. Whoops, I shouldn't show that pi bond. We're forming a new covalent bond here and here between our two sticky pairs of carbons. This pi bond is breaking, this pi bond is being made, and this pi bond's being broken. So can you guys kind of see that transition state? Okay, so now let's finish by drawing our 2D side product. Okay, so this green carbon's now that rooftop carbon. This blue pair formed a covalent bond here, so I'll write new sigma bond right here and here. We've got a new pi bond over here. And then on, oh my goodness, you were right about the methoxy. Let me move this over so I have enough space. So this should be OME. These are our new sigma bonds right here and right here. So I'll just write new sigma. Whoa. Okay, and then we said this methoxy or methyl ester's got to be pointed down, and the other hydrogen's got to be pointed down too. So I'm going to write CO2Me. And then the two hydrogens kind of pointed out in a way like that. Can you guys kind of see that side-on view? These side-on views take a little bit of practice to get good at. But let's now translate that into our 2D view up above and include dashes and wedges where needed, right? Yep.
Why is it pointing down? I'm lost at that.
So you were asking, why is this methoxy pointing down? Yeah, that's a great question. So if we look at this, right, I'm going to highlight this as our green substituent. This is our electron withdrawing group. Our electron withdrawing group prefers to be on the side closest to the longest bridge. So if we look over here, let me find a different color. Should we do sparkly? This gold bridgehead is 2 carbons long, right? As opposed to, let's go with rainbow sparkle. This rainbow sparkle is only 1 bridge long. The methoxy group prefers to be closest to the longer bridgehead. That's our endo orientation, right? Okay, so now let's convert this. I'm going to pretend like we're looking down on this. That green carbon in our 2D view is right here, and we know that that green carbon is kind of like a roof carbon. So what I'll do is I'll draw this as a wedge and really try to show that that's sticking out of the page towards our eyeball, right? Okay, and then our methyl ester is closer to our eye or further away? Further away. So what we can do is we can say, you know what? This should be really represented by a dash coming off of the ring. So we would end up with this as our product. So this would be the correct stereochemistry and regiochemistry. And we would end up with the enantiomer as well. So you oftentimes end up with a mixture of enantiomers out of these. So for example, if the roof is going into the page, you could have that methyl ester coming out of the page as a wedge. So you would end up with a racemic mixture of products out of this. Yep.
So the stereochemistry of the products makes sense, but when you did the mechanism right after the hybrid orbital one, the bottom left corner, why is it pointed towards the molecule if it's going to be under? Shouldn't it not really matter since it's linear or it's planar?
So you oftentimes do end up with a mixture of endo and exo. So you might observe 75% endo, 25% exo. But this methyl ester right here really wants to be underneath the ring when it's docking. And because of that, it's going to end up pointing in this down orientation in the final product.
Yeah, I was just wondering why, because in the one before the transition state, you show it, I guess, under it, but it's towards it, not away from it, I guess. Does it really even matter at that point since it's going to be planar when it docks?
It kind of does. It's hard to show using two-dimensional drawings like I'm doing. If you look in your textbook, it's got a few better pictures. So I would take a look at the endo versus exo section in your textbook to get some slightly better drawings than what I'm capable of doing. Yep.
So what you're saying, like where you have highlighted in gold, so that methoxy, or that
The methyl ester?
methyl ester going down, so if that bridgehead's like this, it's up like this, because these are both down, they're closer than if it was like this, because then that bridgehead would be in between. Is that what you're saying?
Yeah, all endo is saying is this electron withdrawing group, right
It's like within the same plane.
here,
Sort of, it's not exactly the same plane.
wants to be closest to the longest bridgehead.
Right, and it's
That's
like
all
that,
it means.
Then as if it was coming up, because in that bridgehead, the shorter bridgehead would be in between them. And
Exactly. If you had a 2-carbon bridge pointed up, endo would actually be in the other orientation.
Okay.
It's really just the relative positioning of your electron withdrawing group and the
it's
longest
almost kind
bridgehead.
of like they're not separate by their bridgehead.
Yep.
You're saying, so it makes it closer.
Yep.
Okay.
Exactly.
So is that kind of like you have an electron withdrawing group and an electron rich group, and they want to be, are they attracted to each other?
It has more to do with stabilizing the transition state than the overall stereochemistry of the final product. So you want that methoxy group to be underneath in the transition state. All right, the good news is this is as complicated as I'm going to make DielsAlder for you guys. You can actually go into this in a lot more detail. So for example, your dienophile can have an oxygen as one of the atoms. It doesn't always have to be 2 carbon atoms in your dienophile. You can actually have a dienophile that's an aldehyde or something like that. We're not going to get into that very much. There's also inverse demand DielsAlder reactions. So for example, your diene, instead of having an electron donating group, can have a withdrawing group. And your dienophile that normally has an electron withdrawing group can have an electron donating group. So there's a bunch of variations on this, but our textbook doesn't get into it, and I'm not going to spend too much more time on this. Make sense? All right, the last part of the chapter is fun, I promise. It's about colors. So conjugation is closely related to color. If we look at the most colorful natural compounds, they have these alternating double single bond patterns in them, right? And it makes a fair amount of sense. If we look at benzene, benzene's clear and colorless, but as we start adding more conjugation, we start running into these colored compounds like tetracene, which is this brilliant orange-red color. If you continue adding conjugation, it's a little bit bizarre. So I'll show you guys this weird oddity. So in this case, we're getting more red-shifted. And then over here, it all of a sudden switches to going more blue shifted back to the purple side. Does anybody know why? Kind of. It's weird. Pentacene is a really, really unstable molecule. And so I'll redraw pentacene.
Blue light's higher in energy.
Yeah, it's higher in energy, and pentacene is so unstable that it really doesn't like having that alternating double single bond pattern as shown. In fact, a much, much better way of drawing pentacene would actually be like this, as a diradical. So if we look at pentacene, really what's occurring here is that you've got a naphthalene coming off of 2 ends of a diradical cyclohexane. So in this case, when you start adding more conjugation, sometimes you run into these unpredictable patterns where it'll turn more and more redshifted the more conjugation you have, but after a certain point, you're making your molecule so unstable and so reactive, it might actually form a diradical, and these are very, very reactive and will tend to decompose very quickly too. There's a whole bunch of other colors that are common in chemistry, going from blue to purple. So if you've ever worked with indigo, you've seen that blue color. That's due to that alternating double single bond pattern. I know you guys can't see the one underneath it, but that's vitamin A. And then underneath it, we've got beta carotene. That's one we saw in lab. So you can see the more conjugation you add, the more red shifted you normally get. So we're going from blues and purples to oranges and reds by increasing the number of double bonds. If we keep on adding them, once in a while, they'll become so reactive that the color will change back to blue again, so you have to watch out for that. And then if you're in bio labs, you oftentimes have these dyes that you'll load into your cells. Have you guys done that for staining? I think you guys have. Those. Yeah, there's a lot of different stains in biology, and all of them are based off of this increase in conjugation. So the question is, how can we predict what color a compound will be? There's actually this list of rules called the Woodward-Feser rules, where you can take this base value for a conjugated diene and say that that's 217 nanometers. That's going to be your absorption, right? And then if you add double bonds, you're going to add 30 nanometers to it. So it's going to go more and more red-shifted. And then if you add an alkyl group, you're going to add 5 nanometers for each alkyl group coming off of your chain. And then for an exocyclic double bond, you also add 5 nanometers. And then if you've got a homoannular diene where you've got a ring coming off, you want to add 39. These are really easy to memorize, and I'm going to quiz you on them tomorrow. It's a joke. These are just good reference points. More and more, you don't even bother with these rules. You plug it into computational software, and a computer will spit out the best guess for what the color of your compound should be like. However, for a long time, chemists used to rely on these charts for predicting the color of conjugated compounds, if that makes sense. All right. There's one last thing I want to show you for those of you interested in healthcare fields. That's the chemistry of vision. There's a whole section in your book talking about the chemistry of vision, but this is really due to the conjugation of your rods and cones, right? So the rods and cones in your eyes have different lengths of conjugation that are tuned for specific wavelengths of light. So we just said that depending on the extent of conjugation, it will absorb different wavelengths of lights. And then when a wavelength of light hits one of these double bonds, it can actually flip it from cis to trans. And this interaction right here from this big bulky group will hit this protein, or it will be so far away that the protein can't feel it. And basically what that does is it will send a nerve impulse to your brain saying, hey, you just saw this frequency of light, and then it will slowly relax back. If you're blind, oftentimes you've got a defect either in the cone or the rod protein, so this ospin, or you've got some sort of defects with your conjugation. So, for example, if you're born with a birth defect where you're missing a gene in this protein, you might be blind for seeing various frequencies of color. The other interesting thing is that humans have rods and cones. We're really good at seeing a handful of colors, but there are other animals that can see way more colors. So I'm going to show you guys this just because I think it's funny. Has anybody seen the Oatmeal, the comic? Okay. I was disappointed to learn that what I'm about to tell you isn't the full truth, but I still think it's fun. There's this little shrimp called the Mantis Shrimp. And this Oatmeal comic says, why the Mantis Shrimp is my new favorite animal. So our eyes contain millions of these rods and cones. Like I said, rods enable us to see light and motion. Cones enable us to see color. Dogs have 2 types where they can see greens, blues, and a little bit of yellow, which is ironic because you throw a dog a tennis ball, they can't really see it very well. Humans have 3 types of color receptors. We can see green, blue, and red, which is pretty good because then we can combine those to see the hybrid colors. Butterflies have 5 types of color receptive cones, so they can see further into the IR than we can, which allows them to hunt flowers a little bit better. However, the mantis shrimp is way better. So instead of having 2 cones, 3 cones, or 5 cones, it has 16 different cones. So the rainbow we see from just 3 colors, try to imagine that with 16 cones, and they say it's a thermonuclear bomb of light and beauty. So perhaps that's why they're so pretty and glorious to look at. They're really colorful, although I heard they're very toxic too. You have to be very careful around them. So being a creature who perceives such beauty, you'd expect it to be some holy shrimp. However, they're really awful. They tend to fight with one another, and I'll just cycle through this. It's an undersea nightmare, one of the most creatively violent animals on Earth. It's got these 2 things on the front of its body that can shoot out really quick to knock out its enemy or an opponent. And it's stronger than a gunshot from a .22 caliber rifle. 1,500 newtons of force. So we could throw a baseball into orbit if we had that sort of power. The crazy thing, too, I thought was funny, was you can't put them in a fish tank because they'll knock holes through your fish tank. They're incredibly violent. So you can see these are my murder sticks. There are many like it, but this one is mine. And the other interesting moral of this story is that we've been really convinced that humans only have these 3 color receptors until recently. They did this big survey of human beings across the planet, and there are actually a handful of females across the planet. It's like 1 in over 100,000 females that can actually see further into the red than everybody else. And so they can give them these two cards where you look at them and you're like, they're both red. What's the big deal? And they could be like, no, they're totally different. Which is weird to think about, that our species has evolved to potentially have more than these three cones, and we're trying to figure out the full extent to which we're capable of turning that on and off. So maybe in the future we could genetically engineer ourselves to see further into the red region. The other thing too is they're realizing that the mantis shrimp's 16 cones aren't necessarily for 16 different types of colors. It's for a lot of different purposes besides just color perception, but it's kind of an interesting comet to look at. So I think we're going to end there today. There's a handful of practice problems that I posted in the notebook too. If you want to take a look at it, this one's pulled from a previous quiz. I pulled some from the book that are pretty good. And then if you want a real challenge, this one down here is, what's the product for this reaction, and assume you have excess amount of your cyclopentadiene.
What's that 4 plus 2?
4 plus 2 means that it's a Diels-Alder 4 plus 2 cycloaddition reaction. Yep.
You know that's stronger than the pistol shrimp?